So now we'll talk about the energy stored in the electric field or in a capacitor. So, so we know that the potential energy can be written as the integration of du, and then you can simply imagine that you're charging the capacitor, a charge after another from 0 to Q, so that so that the voltage would change gradually, and then of course this V is proportional to the charge amount. So finally it turns out to be Q squared over 2C, or actually you can make use of a Q equals CV, so that we have a C squared over V squared over 2C, so it turns out to be 1/2 ZV squared. So usually we will use U equals 1/2 CV squared in a circuit sense. Of course, in the physics book, this is a physics textbook, it usually uses the Q. So it has an expression like a Q squared over 2C, but usually in a circuit point of view, we only consider RLC, IV, something like that. So that we generally use CV, 1/2 CV squared, for the expression of the charge of the energy stored in a capacitor. So in other sense, this is the energy density U stored in the which is the potential energy stored per unit volume, which will be like this, So actually, this is the U. It tries to divide the volume. For this case, you may imagine it is a parallel plate capacitor, so the volume stored there would be AD. So we have a parallel plate here, and then this volume would be AD. AD as the volume. So U, small u is a capital U over AD, and this is 1/2 CV squared all over AD. And then you know that C is epsilon naught A over D, and then times V squared. V squared is, we also know that V equals E times D. So we have E squared D squared over AD. So we can cancel A and A, DD with this D squared. So it turns out to be 1/2 epsilon naught E squared. So this is the energy density. Actually, I seldom use this one, but it will be useful for explaining the electromagnetic wave in chapter 33. Chapter 33, when we talk about the Poynting vector of the EM field, EM wave. Okay, so this is the energy point of view for the capacitor. So let's take a look at a sample problem. So an isolated conducting sphere whose radius, isolated means the outer one is infinitely large. So it is nothing but 4 pi epsilon naught R. So the charge is Q. How much potential energy is stored in the field, in the electric field of this charged conductor? So first we have a C equals 4 pi epsilon naught R, and and the energy stored is U equals Q square over C. It is not it's not suitable to use a 1/2 over C square, 1/2 CV square, but here we should use this one because in this case V is not quite uniform. So it is better to use this one instead. So it will be, let me see. So it will be Q square over 4 pi epsilon naught R. So Q is 1.2 times, or maybe we have 1 over 4 pi epsilon naught, which is 8.99 times 10 to the 9th power, and then Q square is 1.25 times 10 to minus 9 quantity square, and then R is 6.85 centimeter, which is 0.0685. So it should be 1.03 times 10 to minus 7 joule. So what is the energy density at the, so this is for part A, what is the energy density at the surface of the sphere? So for part B, we have a small u to be 1/2 epsilon naught E square, 1/2 epsilon naught E square. And actually, we have a sphere, this is small r, and we have a Q on this one, so that we can imagine there is a Gaussian surface larger than capital R, which is a small r. So in this case, using the Gauss law, you will know that E of R will be 1 over 4 pi epsilon naught times Q over R square. Or actually, if you make small r to be R, then ER would be 1 over 4 pi epsilon naught times Q over R square. So that we substitute this expression here, we will have Q square over 32 pi square epsilon naught R to the 4th power. So we can simply substitute all the values here. We have a 1.25 times 10 to minus 9 quantity square over 32 pi square times 8.85 times 10 to minus 12 times 0.0685 quantity square, so to the 4th power, So it turns out to be 25.4 times 10 to minus 6 joule per meter cube. Or you can write it as a 25.4 microjoule per meter cube. Okay, so far any questions? So next we talk about the dielectric, capacitor with dielectric. So previously we know that if we want to have a larger capacitor, we can either make it larger, make the surface area, make capital A to be larger, or we can make the two plates closer together, then the capacitor will also be larger. So there is another ways to make the capacitance to be larger. So the point here is we insert something in between the plate. As you can see here on the left side, we have nothing in between the two plates, which is you can imagine there is only air in between the two plates. Now we place something called a dielectric in between the plate. So now suppose the V is constant after inserting the dielectric in the capacitance. The charge here increase. The charge here increase, which means the C really increase. Or in other way, as long as we have already stored some charge here, as long as we already store some charge here, and then we measure the voltage, and if we insert the dielectric in between, the voltage decrease. The voltage decrease, or the electric potential decrease, which means that C increase. C also increase in this case because we have Q equals CV. Q equals ZV. So here Q is a constant, so that V decrease, C increase, V decrease, C increase. And for this case, Q equals CV. Here we have V to be constant, so that Q increase, C increase. Here C increase, V decrease. So this is a constant. And here V is a constant because for this case it connects to a battery, which means the voltage should be constant. So if the space between the plate of a capacitor completely filled by a dielectric material, so the capacitance C in vacuum, 真空, or effectively in air. So in vacuum or in air, the conductivity will be nearly the same. So usually it will mention in vacuum, or it is equivalently to be in air. So it's multiplied by a material dielectric constant, kappa. It is actually a Greek letter, not K. It is kappa. So which is a Greek number, which is always greater than 1. Actually, you can have the kappa, have a material with a kappa smaller than 1, which means that you can make the speed of light to be faster than the real speed of light. Yeah, but actually so far we cannot go faster than the speed of light yet, the vacuum speed of light yet. Yeah, so this point is important. So it tells you that in a region completely filled by dielectric material of an electric constant kappa K, constant kappa, all the electrostatic equation contain the epsilon naught, and then you can replace it by kappa epsilon naught. You just add the kappa there, and that's it. So this is some hardcore physics about the dielectric. So you can imagine inside the dielectric there are many dipoles. There are many dipoles there. If there are no electric field going through it, then they will not align. Every dipole will point to different direction randomly, so that overall all the electric field generated by all these dipole will cancel. It's just like after finish the class, you will not all facing the screen. Maybe during the break, maybe you will talk with some of your friends, or maybe you will go outside. You will be somehow more random. But during the class, you will generally look at the screen somehow like this. If we apply an external E field to the dielectric, then all the dipole will roughly align to a direction following the E field. So in this case, you can imagine, suppose we have a E field pointing to the right side. So for the positive charge, it will go to there will be a force acting to the right side. Suppose an E field. So for the positive charge, there will be a force acting to the right side, and for the negative charge, there will be a force acting to the left side. So it will generally pointing like this: positive side on the right side, negative charge on the left side. In this case, all this dipole will generate is E field pointing to the left, which means that inside this material, part of the external E field, this is epsilon naught. Epsilon naught is the external E field. This E prime is generate by the dipole. As long as they point to the same direction, then the E field generated by all these dipole will add up together. And as long as the right side is a positive side, the left side is the left side is the negative charge, so that the E field generated by this one will point to the left side and cancel part of the E0. So E is the total. E is the total E field inside the dielectric. Inside the dielectric. So dielectric is an interesting material. It's an interesting material. Its behavior depends on whether there are some external E field. If there are no external E field, it will somehow like random, and it will not generate E field, because generating E field needs energy. So if there is no external E field, they will not align each other. Just like if you don't have class, you will not just sit there and then look at the screen. So in this case, we will consider the dielectric and the Gauss law. And originally, the capacitor is like this, and we define the Gaussian surface like this. And if we insert the dielectric in orange color here, then we need to modify the Gauss law. Originally, we don't have this copper, but as mentioned, if we insert the dielectric here, we will replace epsilon naught by copper epsilon naught. So it just write the copper inside the integration, but it's nothing special. Yeah, actually, for advanced electromagnetism textbook, it will use D, electric displacement, capital D, which is like this, but actually it will not use for the rest of the textbook, so it is seldomly used, so knowing this one is quite sufficient for this course. Okay, so nothing special. So let's take a look at an example. So here, a parallel plate capacitor C is charged by a battery to potential V, and its plate, between its plate, the charging battery is now disconnected, and a porcelain slab, so a kind of dielectric, is slipped between the plate. What is the potential energy of the capacitor before the slab is inserted? So before. So it is trivial because it is nothing but let me see, the potential energy. It is UI equals 1/2 CV squared. So substituting the number 1/2 times 13.5 times 10 to minus 12 for the pico, and then times V is 12.5 squared. So it is 1.055 times 10 to the minus 9 joule. So it is easy. So the next one for part B, so what is the potential energy after the slab is inserted? So now we know that as long as we have C, actually we have C should be epsilon naught A over D, although we don't really need to use this one, but this is for a vacuum. So as long as for this case we have C prime equals copper epsilon naught A over D, which means that C prime should be copper epsilon naught, copper C, copper C. So you just multiply the C by a copper, then it will be the new capacitance C. So it will be 6.5 C, 6.5 C. So actually only for inserting this lap, then the capacitance is increased by 6.5 times. And the potential energy would be, the Q doesn't change. Actually, the V will change. Because it tells you that it is disconnected. For that case, it is like we charge, there is some charge, Q, positive side Q, and then negative minus Q, and then disconnected. So there will be no charge can going in or out. So for this case, we still have the same amount of charge. The charge cannot change. And the C increase. Also the V will increase. so that we cannot use Vf equals 1/2 CV squared because we already changed. So this is not good for this case. So we use Q squared over 2C prime. So the Q doesn't change, which is 13.3 times 10 to minus 12 times 12.5. So this is the original charge, 13.5. So this is the original charge and it doesn't change. And then it is 2 times 6.5 times 13.5 times 10 to minus 12. So it will be 1.62 times 10 to minus 10 joule. So you can see that originally the potential energy is larger, 10 to minus 9. This is 10 to minus 10. So this is smaller than the previous one. So which means that, which means that, so actually, we can also calculate that W is UI minus UF, which is 8.93 times 10 to minus 10 joule, which means that the E field will actually do some work to make this slab slide into it. There may be two cases. You need to spend some force, you use some force to put this slab in it. But the other case is, if you place this slab close to the capacitor, this slab will automatically slide in, and then the energy goes to this dielectric, and then in the capacitor system, the stored energy reduces, because for this dielectric it will generate some E field to cancel some of the E field, so that some energy goes to the dielectric. So the next one is so here we have a parallel plate capacitor, area A and the separation D. So a potential difference V0 is applied between the plate. The battery is then disconnected. So the dielectric slab thickness B. So this is A, this is B. And the dielectric constant K is placed between the plate. So we assume A, D, V0, B, and copper to be like these values. So what is the capacitance? C0 before the slab is inserted. So similarly, we can simply calculate by C0 is epsilon naught times A over D. So it is nothing but 8.85 times 10 to minus 12 times A is this one. So it should be 115 times, let me see, 10 to the minus 4 power to convert it back to meter square. So this is meter square, should be the SI unit. And then D is 1.24. So C0 is 8.21 picofarad. Okay, so this is a simple one. So the next one, what is the free charge appear on the plate? So it's asks you what is Q. So Q should be Z0 times V0 times V0. So we know that C0 is 8.21 times 10 to minus 12 times V0 is 85.5 volts. So Q0 would be 7.02 times 10 to minus 10 coulomb. So this is still another simple question. So the next one, what is the electric field E0 in the gap between the plate and the dielectric slab? So it asks you the E before, of course. This is also assuming that before the slab is inserted, or actually it asks you E0 is here, E0 is here, E0 is here. And of course, inside the dielectric, the electric field is smaller. So now we calculate E0 and calculate E0. So we can use the Gauss law. Let me see. So we use this Gaussian surface 1. We can have epsilon naught integration of E dot dA equals Q. So this is, so within this Gaussian surface 1, Q enclosed is plus Q, and then E0 pointing to the bottom. So we have epsilon naught E0 A equals Q. So it is nothing but E0 equals Q0 over Q over epsilon naught A. So Q is 702 times 10 to minus 12, and then 8.85 times 10 to minus 12, and then A is 0.0115. So this one is 6,900 volt per meter. Yeah. So this is still a simple one. So next one, what is the E field? What is the E field E1 in the dielectric slab? So just now we have a E0 here, E0 here. It asks you what is E1 inside the slab. So here we apply the Gauss law to GS2. So we have epsilon naught integration of kappa E dot dA equals, this one is enclosed here, so it should be negative Q. So although it asks you about all this, it's right plus Q prime there, but we should omit that part for this moment. So we can see that for this side there will be no E field, and then this side no E field either, this side no E field either. So the only one is this side, and then E1 is pointing downward. However, dA should be pointing upward. Which means that this should be a negative value. So we have negative epsilon naught kappa E1 dot, not dot, times A equals negative Q. So E1 will be simply Q over kappa epsilon naught E1, A. So we can substitute the number, this is a 702 times 10 to minus 12 over kappa is 2.61 for this problem. And then epsilon naught is 8.85 times 10 to minus 12. This is a 0.0115. So E1 is much smaller, which is 2640 volts per meter. So much smaller, or 2.6 times smaller. This is 6,900. This is 2.6 4,000. Okay, so next one we can calculate the potential difference between the plate after the slab has been introduced. Similar to the previous sample problem, as long as we disconnect the capacitor and then insert the slab, which means that after inserting the slab, the potential difference between the two plates will change. So now, after getting the E1 and E0, so we know that E1, we already know E1 and then E0. Then we can calculate the V by integrating EDS from negative to positive plate. So actually the E field is uniform, at least in this region, so that this line integral is nothing but multiplication. But we need to separate into two parts. For the orange part, it will be E1 times B. B is the thickness of this dielectric, and then for the rest will be D minus B. We don't really know that how long is this one and this one independently, but at least we know that the total distance for this one and this one will be D minus B. So it's enough. And then we have E0 times D minus B. So that we just plug in all the values. E1 is 2640 times B is 0.0078 plus E0 is 6900, and then D is 0.0124 minus 0.0078. So it turns out to be 52.3 volts. So originally V0 is 85.5 volts. So now it becomes 52.3 volts. So the final question is, what is the capacitance with the slab placed between the plate of the capacitor? So now we simply calculate the C. The new C will be Q. Q doesn't change. And then this is a new V. So Q is 702 times 10 to minus 12 over, this is 52.3 volt. So finally it will be 13.4 picofarad. Originally it is 8.21. 8.21. C0 is 8.21 picofarad. So it becomes larger. So maybe I have a little bit more comment about this plus Q prime. This is a tricky question. Somehow very hardcore physics problem. You may ask why we don't include a plus Q prime here. Actually, you can finally find that there will be a plus Q prime there, but actually when we use this Gaussian law and then include this area, we will exclude this term because when you consider the overall dielectric, it turns out to be there will be some charge here and some charge there. However, you can consider that for this case, if you just pick these parts, actually there are some dipoles there. However, the total charge there is zero. So the Q prime is somehow like the equivalent charge at that part. However, when you really want to calculate how many charge in that region or in that volume, it should be null, because the dipole is like the two charge with opposite side placed close together. So if you just include a slightly larger area, then the total charge should be zero. So that's why here we do not include the plus Q prime for this part. Although in the textbook we also have a formula to calculate what Q prime is. It is not that small, but actually considering the Gauss law, we already calculate kappa there, so that if you also have the plus Q prime there, then it will be wrong, because you account the same issue twice, which is not good. If you don't have a kappa there, then you can have a plus Q prime, so then you can find the equivalent Q for this dielectric, but you don't try to account the same issue for two times. That's my understanding. So, and this is the end for this chapter, and I'll see you tomorrow.